All right. Good morning, everybody. So I hope you can hear me. Good morning, and I hope you are having a good day. Sana hindi pa kayo nalulunod sa mga requirements. But anyway, it's almost the weekend. The weekend is just around the corner. So let's sustain your good morning by talking some more math, right? What a better way to enjoy this nice morning than to talk some math, right? Some real analysis. So last time we talked about the completeness axiom, right? And we said this is the distinguishing characteristic of the set of real numbers. So maraming mga ordered fields, right? So we have seen a couple of them: the set of rational numbers, the set of algebraic real numbers, then the real numbers itself, right? But what's very special about the set of real numbers is that it is complete, right? But again, we want to give a meaning dun sa ibig sabihin ng pagiging complete. Well, in layman's terms, parang ano lang siya, kompleto na. Wala nang kulang dun sa set of real numbers. But mathematically, we need to quantify or we need to give a specific and a tangible meaning kung ano yung pagiging kompleto ng set of rational numbers. So, hindi pwedeng sabihin natin na kompleto siya kasi wala nang kulang sa kanya. Pero kulang in what sense, all right? And we try to give a characterization of it, of completeness, and that's through A12, which is the notion of completeness broached by Dedekind, right? So sabi ni Dedekind, kung mapapartition mo ang isang set into kung mapapartition mo ang isang ordered field into two sets, tawagin mong set A and set B, such that uh, lahat ng elements ni capital A ay mas maliit sa lahat ng elements ni capital B. Then complete yung ordered field na yon if you can find one member of that ordered field that will serve sort of as a boundary. In the sense na lahat ng mas maliit dun sa unique na member ng ordered field na yon ay element ni capital A, at lahat ng elements ng ordered field na mas malaki dun sa boundary element na yon ay element ni capital B. Alright? So in this illustration, siya si little c. Siya yung nagiging boundary. Lahat ng nasa kaliwa niya ay member ni capital A, lahat ng nasa kanan niya ay element ni capital B. And if that happens, so if you can find such a unique number in your ordered field that satisfy that requirement, then what you have is a complete ordered field. All right. And we said it can be assumed rightfully for the set of real numbers, and that's what we say, what we call the Dedekind completeness axiom. But for smaller ordered fields, hindi nila nasasatisfy itong completeness axiom, right? Ang example natin last time ay sa set of rationals. Pinakita natin na kaya nating i-partition yung set of all rational numbers in such a way that it satisfies condition 1 and condition 2 nung A12, pero wala tayong mahanap na rational number na magsiserve as the boundary that will serve as the number C in this illustration, okay? And specifically, that is the set A, which contains all rational numbers that are less than square root of 2. And set B is the set of all rational numbers that are greater than or equal to square root of 2, right? So, ang makikita natin dito na posibleng mag-serve as the boundary that will satisfy Dedekind's completeness ay si square root of 2. But unfortunately, si square root of 2 ay hindi rational number. So therefore, kulang si Q. Kulang yung set of rationals kasi walang magsiserve as boundary kapag ito yung kinonsider ko na Dedekind cuts. Alright? So kasi si square root of 2 was proven to be an irrational number. Wala siya kay Q. Alright? So kaya sabi natin, yeah, ordered field nga si Q, pero hindi siya complete. The same thing will happen for the algebraic real numbers. Kasi nga, remember, ang algebraic real numbers, sila naman yung set ng mga solutions ng polynomial equations with integer coefficients. Now, I can produce a partition of the set of algebraic numbers. Tawagin nating curly A, yung set of algebraic numbers. So, kunin ko lahat ng algebraic numbers na mas maliit kay pi. Tawagin ko siyang set A. So, ito si set A. Tapos si set B, lahat naman ng mas malaki kay pi. Alright? Now, the only possible boundary point that can satisfy the completeness axiom ay si pi. Alright? Kaya lang ang problema, si pi ay hindi algebraic number. Okay? So because there's no polynomial equation that whose solution is pi. Alright? So, isa siyang transcendental number. So, kulang pa rin yung ordered field of algebraic real numbers. So kailangan pa natin silang dagdagan, and ultimately, to complete these ordered fields, ang kailangan natin talaga ay set of real numbers. Okay? Now, graphically, the completeness axiom by Dedekind seems to be very simple, right? Ang dali niyang i-visualize. Magkakaroon ka lang ng dalawang ray. Yung isa, ray na papunta indefinitely pakaliwa. Yung isa, ray na indefinitely papunta sa kanan. Okay? Tapos dapat lagi kang may boundary point sa pagitan ng dalawang ray na yon. Okay? Now, yeah, it's intuitive, it's geometrically making sense, but the problem is it's very hard to operationalize. Mahirap siyang gamitin sa mga proofs because it is very abstract. Okay? Now, in view of that, siguro sa Math 155 at this particular level, since we are just studying advanced calculus as beginners, okay? Siguro kailangan natin ng mas analytic o mas operationalizable o mas madaling i-utilize na completeness axiom, all right? So, hanap tayong ibang version para sa A12 or para sa completeness axiom. And I think one of the simplest versions of the completeness axiom is the LUB property or the least upper bound completeness axiom. Okay? Tawagin ko siyang LUBP or LUB property para mas maikse. Okay? Now, the LUB property is equivalent to the completeness axiom in the sense that Dedekind's completeness can be used to prove the LUB. Pwede nating i-treat as a theorem yung LUB property kasi provable siya using the completeness axiom, right? Ang kagandahan lang sa LUB property ay pwede naman nating i-prove yung Dedekind completeness gamit ang LUB property. So we can assume the LUB property and prove Dedekind's completeness. So in other words, we are basically we basically have this this equivalence, right? So we can put the LUB property into a biconditional statement with Dedekind's completeness, all right? So ibig sabihin, they are logically equivalent, so they could be interchangeable, all right? Kailangan mo nga lang sigurong i-shuffle yung mga undefined terms o yung mga definitions. But basically, if we will replace Dedekind's completeness axiom by the LUB property, then we will get the same theory. Okay? Kasi equivalent sila, one is provable from the other. So lahat ng posibleng theorems na ibigay ni Dedekind completeness ay kaya rin nating ma-deduce mula sa LUB property. Okay? However, we cannot put together yung Dedekind's completeness at saka yung LUB property sa list of axioms natin. Bakit hindi natin sila pwedeng pagsabayan na axioms? Do you guys remember? Baka isipin niya, sige, para na lang sir, walang away, parehas na lang silang axioms. Bakit hindi pwede na silang dalawa ay gamitin nating axioms na magkasabay? Yes, David?
Sir, kapag axiom po yung isa sa kanila, the other one, para maging axiom yung isa pa, it shouldn't be able to be proven using the already existing axioms.
Okay, perfect. That's right, David. So sa isang ideal axiomatic system, we want the axioms to be independent from each other. We don't want one axiom to be provable using another axiom and vice versa. Kaya nga nilagay natin sa pedestal yung axioms. Sila yung mga bagay na hindi natin pinuprove, either they are very basic or that we are assuming them for the sake of what is to follow. And to minimize the number of axioms in our system, we don't want to put an axiom that is provable using another axiom para sa independence, okay? Pero makita nyo later, mas madaling gamitin yung LUB property kesa sa Dedekind's completeness kasi nga medyo geometric yung madaling visualization ng Dedekind's completeness, alright? But the problem with the LUB property ay meron tayong mga dapat daanang definitions before we can state the LUB property, which we haven't given before. So let's take a look at them, starting with definition 5. So in here, we are assuming we have a set of real numbers, okay? Then a number little a is an upper bound for the set S if little a is larger than or equal to all members of capital S. Which kind of makes sense. Upper bound nga ang tawag sa kanya. So magiging upper bound siya kapag ka mas malaki siya sa lahat ng members ni capital S. Alright? Now, there would be infinitely many upper bounds as we will see in one of the remarks later, pero merong isang special na number among all of the upper bounds for a particular set. And we will call that the least upper bound of the set. Or if you want to be fancier about it, we call it the supremum of the set. Or minsan sup na lang yung basa. Or our symbol for the LUB or the least upper bound or the supremum of a set S is sup of S, read as the supremum of S. Okay. Well, essentially, the supremum of S is the smallest upper bound. Okay. So kaya nga least upper bound yung pangalan, LUB. So siya yung pinakamaliit na upper bound, pinakamaliit na mas malaki sa lahat ng mga elements ni capital S. Alright? So that means the supremum is an upper bound itself, but it is smaller than any other upper bound for the set S. Okay? Nilagay ko pala dito yung notation. Sorry, spoiler. Okay? And then similarly, you can replace the mention of an upper bound by a lower bound. Pag lower bound naman siya ng isang set, ibig sabihin yung number na yon ay mas maliit sa lahat ng mga members ng set na yon. And then there would be infinitely many lower bounds. Okay? Tapos, ang pinaka-special dun sa mga lower bounds na yon ay yung pinakamalaking lower bound. Okay? And the largest lower bound or the greatest lower bound or the GLB is also called the infimum or the inf of the set S. And we will denote the infimum by inf S, right? So siya yung infimum ni S. Okay? So yung ibang tawag LUB of S, yung iba GLB of S. But let's talk mathematical terms here. Tawagin natin silang supremum at saka infimum ng set S. Okay? Now, definition 1.6, a set S is bounded above if we can find an upper bound. Tapos siya naman ay bounded below pag meron tayong nahanap na kahit isang lower bound. Okay? Now, some quick remarks here. Yung remark 1.8.a, sinasabi niya lang yung infinitude ng mga upper bounds. If a set has one upper bound, okay, then meron din siyang infinitely many upper bounds. Kasi lahat ng numbers na mas malaki dun sa upper bound na nakita nyo, dun sa isang upper bound na kilala nyo, lahat ng numbers na mas malaki doon ay upper bounds pa rin by transitivity of the less than relation. Tama? Ganun din sa lower bound. So pag may nakita kang isang lower bound, lahat ng mas maliit dun sa lower bound na yon ay lower bound pa rin. So if a set has one lower bound, then it will have infinitely many lower bounds. Okay? Kaiba naman yung sa supremum o dun sa infimum. Pag nag-exist ang supremum o infimum ng isang set, unique lang yon. Okay? Because if you assume for the sake of contradiction that there are two, say, suprema, B1 and B2, then B1 must be less than or equal to B2, right? Kasi sabi mo si B1 siya yung least, isa siyang supremum. So ito ay isang least upper bound. So siya yung pinakamaliit sa mga lower bounds. Pero si B2, dahil inassume natin na supremum din siya, so ibig sabihin siya rin ay upper bound. Eh si B1 nga, least upper bound. So ibig sabihin si B1, mas maliit kay B2. Pero parehas nga silang suprema. So si B2 ang pinakamaliit na upper bound. Si B1 ay supremum, so isa rin siyang upper bound. So dapat si B2 less than or equal kay B1 din. Alright? Because B2 is a least upper bound. But if we put together these two inequalities, that will mean that B1 is equal to B2. Alright? So that's why we will be using the article the, kasi unique ang supremum. There cannot be two suprema for a certain set. Okay? Pwedeng wala siyang suprema, okay? Walang supremum, pero dapat nag-iisa lamang yung supremum. Okay? And then remark C, yung number m sub 0 na supremum ng isang set ay magiging member lamang ng set kung siya ay maximum ng set A. So here we are distinguishing the maximum of a set from its supremum. Yung maximum kasi ng isang set, dapat nandun siya sa set. Alright? So pipiliin mo lang ano yung pinakamalaking laman ng set A. Siya yung maximum. Alright? Pero kung merong maximum yung set A, yung maximum na yon, siya rin yung supremum. Okay? The supremum will be equal to the maximum. And we can say that the supremum belongs to the set A. However, the supremum need not be part of your set. Okay? Kapag yung supremum mo ay hindi element ng set, ibig sabihin walang maximum yung set. Okay? Because of remark C. Well, kailan ba walang maximum ang isang set? Halimbawa, wala siyang maximum pero meron siyang supremum. Halimbawa, open interval 0, 1. Okay? So remember from our notations before, the open interval 0, 1 is the set of all real numbers strictly between 0 and 1. Now, what is the maximum of this set? Ano yung pinakamalaking miyembro ng set na to? Can anybody guess? Ano yung maximum nitong set na to? Get the maximum of the open interval 0, 1. Ano yung pinakamalaki niyang miyembro? Or meron ba siyang pinakamalaking miyembro? Anyone? Or dapat sa mas madali pa lang example ako nagsimula? Hula guys, wala namang minus kapag mali yung hula. Oh yes, Michael?
I think sir wala po kasi although merong pong 1 dun sa interval po 0 to 1 pero hindi po siya included.
Yeah, that's right, Michael. Parang ang hirap i-explain, no? Pero I hope ano siya, intuitive siya, no? Pero parang ang hirap i-explain. Hanapin natin yung pinakamalaking member ni 01. Sige nga, try natin. 01. Kasi alam natin parang finite naman yung interval 01. May katapusan siya, kaya natin siyang i-drawing. Kaya lang, hindi kasama si 0 at saka hindi kasama si 1. So in the search of a maximum for this interval, we need to zoom in doon malapit kay 1. Kaya lang pag sinabi ko na ito yung maximum niya, pag nag-zoom in pa ako, meron pang number dun sa gitna. Alright, sa pagitan nila. Ano ba sabihin ko, 0.999999999 yung maximum. Magdagdag lang ako dyan ng isang 9, mas malaki na siya dun sa previous hula ko. Right? Tapos, sige, kung hindi pa pala ito yung maximum, magdagdag pa ako ng isang 9. Mas malaki yan dun sa previous hula. Magdagdag pa ako ng 9. Magdagdag pa ako ng 9. But this process will not terminate. Alright? Hindi tayo matatapos. So, ibig sabihin, walang maximum yung set na to. So, wala siyang maximum, pero meron siyang supremum. Right? So, the maximum does not exist. But it has a supremum. Ano yung supremum ng set na to? Sige, hula. And then, paki-explain kung bakit. Kung bakit ang supremum niya ay yung hula niyo. Sayang no, nadugsong ko kaagad yung Y. So what's the supremum of the open interval 0, 1? Come on, guys. Bigay nyo lang yung mga upper bounds. Sige, simulan natin sa madali. Give me an upper bound for the open interval 0, 1. Okay, tingnan muna natin yung mga upper bounds niya. Can anybody give me some upper bounds? Yes, David?
5 po, sir.
Sorry, what's that?
5 po.
5, okay. Can you give some more? Probably 2 more?
4 tapos 3 po.
4 at saka 3. Talagang inunti-unti ni David. Okay, thank you, David. Michael, can you give some more?
At 2. 2 po, sir.
2. Ano pa? Nahiya ka pang idagdag yung isa. Bakit walang nagsagot ng controversial na 1? Ba't iniwasan nyo si 1? Nandun na kayo kay 4, nandun na kayo kay 3, 2. Tinigil nyo pa kay 1. Ba't nyo tinigil kay 1? Are you not sure if 1 is an upper bound? Definitely, 1 is an upper bound. Tama? Kasi si 1, mas malaki siya or equal sa lahat ng members ng open interval 0, 1. So definitely 1 is an upper bound. But can we find a smaller upper bound than 1? And unfortunately, we cannot find a smaller interval as a smaller upper bound than 1. Kasi pag binawasan natin ng katiting si 1, magiging member na siya ng open interval 0, 1. At pag naging member siya ng open interval 0, 1, definitely there will be an element of the open interval 0, 1 that is larger than the new number that we have. Okay? So, limbawa, si 1, binawasan mo ng konti, ginawa mong 0.9 followed by 10 zeros. Yung 0.9 followed by 9 nines ay mas maliit kaysa sa 0.9 followed by 10 nines. So yung 0.9 followed by 9 nines ay hindi na siya upper bound. Okay? Pero ang lower bound niya ay si 1. Ang least upper bound pa rin niya ay si 1. Kasi wala na tayong mahanap na upper bound na mas maliit kay 1. Because kung meron mang upper bound na mas maliit kay 1, ibig sabihin papasok na siya dun sa open interval 0, 1. Pag pumasok siya dun sa open interval 0, 1, patay na siya kasi lagi tayong may mahanap na number sa pagitan nung number na yon at saka ni 1, making that smaller number than 1 not an upper bound for the set open interval 0 to 1. Okay? So ito yung isang example ng isang set na may supremum pero walang maximum. Okay? Kaya medyo magkaiba yung terms na yun. So yung maximum, minimum, iba siya dun sa supremum at infimum. Okay? Maximum and minimum must live inside the set, but the supremum and infimum need not be in the set. Okay? All right, there's a quick example here. The open interval 0, 1, its supremum is equal to 1. Then there is a proof given here. Pero ito yung ina-explain ko kanina. There are 2 possible ways to prove it. Okay. Let's see. Kaya lang iba pala to, no? Closed interval 0, 1 yung ginamit. So this is much easier than the open interval. First method is to use the definition. It is clear that 1 is an upper bound of E because remember by definition of the closed interval, this is the set of all x's such that x is strictly between 0 and 1. So, ibig sabihin, lahat ng x na nasa set na to ay less than or equal kay 1. That makes 1 an upper bound of the set E. Alright? Now, kunwari, meron pang isang upper bound si E. Kung may upper bound pa si E, so ibig sabihin si M dapat greater than or equal kay X. So kung si M ay isang upper bound ni E, by definition ng pagiging upper bound, dapat si M greater than or equal sa lahat ng x's na naka E. Pero dahil si 1 ay member ni E, ang E natin dito ay yung closed interval, alright? So siya si E. Ibig sabihin si M ay greater than or equal to 1. Ibig sabihin si 1 ay isang upper bound, pero siya ay less than or equal to sa lahat ng iba pang upper bounds. And essentially, that's the very definition of being the least upper bound. Okay? So, ganun yung proof using the definition. But you can take advantage of remark 1.8c. Alright? Alam natin ang maximum nito. Meron siyang maximum. May pinakamalaking member, si capital E. Ang pinakamalaki niyang member ay si 1. Yung right-hand yung right-hand endpoint niya. Ang pinakamalaki niyang member. By remark 1.8.c, which tells us that if the maximum exists, then that will also be the supremum. So pwede nyo lang siyang gamitin. Oh, okay. The supremum is equal to the maximum. All right? Okay. So, any questions? Clear ba yung mga upper bound, lower bound, infimum, supermum, or you need some more examples? Clear naman yung definition? Okay. Inisip kong ibigay, okay lang ba na yung homework nyo for Monday? Ang ibigay ko ay about supremum, infimum. Magbigay ako siguro ng ilang sets. Tapos hanapin nyo kung ano yung supremum, infimum kung meron man. Or sabihin nyo kung wala. Okay lang ba yan? Or mas gusto nyo mag-prove ng mga abstract na concepts? Sige, ano na lang muna. Sige, supremum, infimum yung paglaruan natin sa homework, right? Pag-isipan ko pa kung lahat ay fill in the blanks o identification or may mabilis akong ipapaprove, alright? Pero sige, para makapahinga naman kayo sa proving, medyo dalian lang natin. Alright. So now I think with this terms defined, we can now look at what is the LUB property, which will be our substitute to Dedekind's completeness. Tawagin natin siyang A12 prime, pero babanggitin ko naman na LUB property or LUB axiom siya just to differentiate it from the Dedekind's completeness axiom, right? So ano yung sinasabi ng A12 prime? Anong LUB property? So, sige, nakalimutan ko palang i-edit yung notes. Tinatawag ko siya kasi siyang LUB property instead na LUB completeness axiom. Masyadong mahaba yung LUB CA. So, LUBP na lang. Okay. So, if you have a non-empty set of real numbers, which is bounded above, then it must have a supremum. Okay. So, yun yung sinasabi ng least upper bound property. Non-empty set of real numbers. Pag may nakita kang isang upper bound, sure tayo na meron siyang least upper bound. Okay? And this will work for the set of real numbers. And siguro, nakasulat na pala siya dito, yung least upper bound niya ay real number din. Okay? So, ang LUB property, pag meron siyang upper bound, dapat sure na tayo na meron siyang least upper bound. Okay? And that's another sense of completeness. Well, this thing will not be true for rational numbers. So pag pinalitan nyo yung real numbers dito sa A12 prime, pinalitan nyo ng rational numbers, in-expect natin hindi magiging totoo yung statement. Kasi nga, equivalent to sa Dedekind's, napakita natin na yung rationals hindi niya nasa-satisfy yung Dedekind's axiom. So ibig sabihin, di rin niya dapat masatisfy yung LUB property because they are equivalent to each other. Alright? Now, a quick counterexample na hindi to masasatisfy ng rationals kasi magiging statement ng LUB property. Suppose S is a set of rational numbers which is bounded above. Then S has an upper bound in Q. Yun yung restatement nito para sa rationals. But if you consider the set S to be, say, the set of all rational numbers such that X is, say, less than 5, for instance, okay? Ito ay may upper bound. Obviously, it has an upper bound in Q. Can you give me some upper bounds? Upper bounds kay Q. All right? Para masabi na nasatisfy natin yung premise ng LUB property. Tinga, bigyan niyo ako ng upper bounds ni S kay Q. Okay guys, sayang yung bonus points. Kahit maliliit yan, baka siya yung pantawid nyo sa I think last semester, the biggest bonus I gave is 1% sa final grade. So, malaki-laki yon. Okay, thank you, David. That's correct. How about the others? Sayang yung bonus points. Ayaw talaga magsalita? Or nagne-Netflix na kayo dyan? Daya nyo, ha? Okay, David is right. 4 is an upper bound. 5 is an upper bound. 25 over 2 is an upper bound. 10 million is an upper bound. 10 billion is an upper bound. 10 billion over 22 over 7 is an upper bound. So there are infinitely many upper bounds. Okay? But the problem is, meron ba siyang supremum kay Q? All right. Obviously, hindi natin magagamit yung trick na ginamit natin kanina dun sa open interval na sabihin si pi yung upper bound. Kasi si pi ay hindi rational number. Okay? Hindi rational si pi, so hindi siya pwedeng maging supremum. Kasi nga ang usapan, ang LUB property, ginagaranti niya na nandun sa parent set yung supremum. So naghahanap tayo ng supremum dapat kay Q. Si pi hindi na pwede. Pwede niyong sabihin, oh sige sir, edi si 3.14 posible. Baka siya yung maging supremum. Alright? So, but however, hindi ito upper bound in the first place because 3.141 is also in the set S. Kaya lang, si 3.141, hindi rin siya upper bound kasi nga na meron ka pang 3.1415 doon sa set S. Alright? So, hindi to upper bound, so hindi na siya pwedeng maging, hindi to upper bound, so hindi na siya pwedeng maging supremum. Okay? Kasi para maging supremum, dapat upper bound ka muna. So, ito na yung next candidate para maging supremum. So, check natin, siya ba ay upper bound? Unfortunately, hindi siya upper bound kasi si 3.14159, nandun pa rin siya dun sa set S. So, hindi na to pwedeng maging supremum. This last guy over here cannot be a supremum either because 3.141592654 is also in the set S. And this process will continue on forever kasi nga non-terminating, non-repeating yung decimal digits ni pi. So we cannot find a rational number that will be a supremum of this bounded above set of rational numbers. So therefore, the set of rationals really doesn't satisfy the LUB property, which should have been expected because we have shown before na si rationals hindi siya complete in the sense of Dedekind. Yung Dedekind completeness, equivalent siya sa LUB property. So hindi rin to masasatisfy ni Q. So parang ito yung nagiging notion natin ngayon ng completeness. Hindi kompleto si Q kasi hindi niya member yung supremum ng set na to. So kulang siya ng isa pang element. So which happens to be pi, which is not a member of Q. So parang ang chine-check natin kung kulang, nandun ba yung supremum ng kahit anong non-empty set ng isang non-empty subset ng parent set na pinag-uusapan natin. Right? But the LUB property guarantees na kapag ka meron kang bounded above na set of real numbers, lagi kang may supremum na real number din. Okay? So ibig sabihin, any set of real numbers that is bounded above has a least upper bound. Okay? And then remark 1.9, I have said it over and over again. So isa lang yung pipiliin natin to be our axiom. So let's pick the LUB property as our default completeness axiom. So siya yung gamitin natin completeness axiom. Now, there are several other statements that are equivalent to the LUB property and hence are also equivalent to the completeness axiom of Dedekind. Marami pa yan. And some of them we will meet later in the course, all right? Tapos ipoprove natin sila probably using the LUB property. Ang ilan sa kanila, Cauchy's convergence criterion, nested intervals theorem, the monotone convergence theorem, the Bolzano-Weierstrass theorem, the intermediate value theorem, finite covering theorem, and a lot of them. I think the Archimedean Principle, hindi ko pa pala nasulat. Ano pa nga ba? Basta marami pa. All right. Not only in real analysis, but also in topology, in functional analysis, and so on. So in our convention, we will consider these guys as our theorem, as our theorems, and the LUB as our axiom. But other books might elect to use, say, for instance, they can use the intermediate value theorem as their axiom, and they will get the same theory as we have kasi nga equivalent lang yung mga axioms na ginamit natin. Doon sa mga nakalista sa number 2, lahat may encounter natin later, probably except the finite covering theorem. So lahat ito ipoprove natin using the LUB property or the LUB properties consequences. Right? So para natatandaan ko nung masters na yata, preparing for the comprehensive exam, kailangan kong sauluhin yung proof ng, I think there are 12 famous equivalent statements to the completeness axiom. Tapos, kailangan naming i-prove, o pinaghandaan ko, na i-prove yung equivalence ng 12 na lahat sila equivalent sa isa't isa. Remember, pag dalawa, madali lang i-prove yung equivalence. So, kung meron kang theorem A, tapos equivalent siya kay theorem B, edi i-prove mo yung biconditional. Prove that A implies B and B implies A, then you're done. You can say that the two are equivalent. Kapag tatlo, may shortcut pag tatlong theorems yung gusto mong i-prove na equivalent. So you can prove that A implies B, B implies C, and C implies A. So you kind of have a cycle here para mapakita yung equivalence. Alright? Kasi nga kung gusto mo i-prove na A implies C, gagamit ka na lang ng transitivity. A implies B, but B implies C. So therefore, A implies C. So nakompleto mo na yung A if and only if C. Alright? So, ganyan pag tatlo. So, meron kang ilan? Isa, dalawa, tatlong ipoprove. Pag apat, komplikado na. So, dadagdag ka rito ng isa pa. So, meron kang apat na basically kailangang i-prove. So, pag 12 na sila, na isa sa mga traumatic experience siguro, pero fulfilling siya. Alright, so kailangan mong isipin sino yung ipoprove ko using yung isang result. Kasi baka naman yung proof nung A to C ay mahirap. So kailangan talaga dumaan ka sa A implying B at saka B implying C. So, but for us, we will not do that. I will not ask you to prove the equivalence. Susundan natin sila sequentially. So alam na natin mag-start tayo sa LUB property and we will try to deduce the other pertinent theorems that were listed in remark number 2. Okay. Now that's the LUB property and a little bit of background about it. So tingnan natin yung consequences ng LUB property o ng completeness axiom. Right. I think the most immediate one is corollary 1.1, which is basically translates LUB property in terms of the infimum. All right. So pag restate natin yung completeness axiom in terms of the infimum, ganito yung magiging itsura niya. But we cannot admit this as another axiom kasi provable siya using the LUB property. All right, makikita natin yung proof dito sa handout. But let's see how it reads. So suppose this is a non-empty set of real numbers which is bounded below. Bounded below naman siya. Dahil siya ay non-empty set of real numbers, then the set S will have a greatest lower bound that is another real number. And since this is a corollary, a direct consequence of the previous theorem, which happens to be the LUB property or the previous axiom, the completeness axiom, right? So, dapat straightforward yung pagkaka-apply ng completeness axiom with just a little bit of a trick para ma-prove si corollary 1.1. And it has a nice trick here. So let's read the proof. So, ang alam lang natin kapag ka may upper bound, meron siyang least upper bound. Ang gusto nating i-prove pag may lower bound siya, meron siyang greatest lower bound. So, ito yung trick. Kailangan kong i-translate yung set S, yung mga properties ni set S in terms of a supremum or infimum of another set. And it's kind of easy to do. So, kung meron akong set S na non-empty, i-form ko lang si set T. Ano ang laman ni set T? Lahat ng negative x's, where x is an element of capital S. Now, baka may hangover pa kayo from the very axiomatic development of R. Etong negative x, ito na yung usual negative notion natin ng numbers, right? So kung meron kang 5 kay S, halimbawa, so si negative 5 na kay T. Additive inverse pa rin naman siya, pero pwede na natin siyang tingnan in the naive way na tinignan natin yung mga negative numbers before. So parang ninegate ko lang yung mga elements ni S. Okay? Now, sabi si set S daw, meron siya bounded below. So meron siyang lower bound. So let's let L to be a lower bound for S. Kasi nga bounded below si S, so meron siyang lower bound. So ibig sabihin, there exists a real number L such that little l is less than or equal to little s for all s in capital S. All right? Kasi nga lower bound si little l. Tapos properties of inequality. We can multiply both sides of this inequality by -1 and have negative L, mababaligtad yung inequality, kakaroon ka ng negative S. Alright? But S is a member of capital S. So therefore, yung negative niya ay dapat element ni capital T. So sinasabi natin dito ay lahat ng elements ni capital T ay mas maliit kaysa kay negative L. So that means negative L will serve as an upper bound for the set T. So meron tayong set T, non-empty. Tapos meron siyang upper bound, si negative L, yung negative ng ng lower bound ni capital S. So by the LUB property, dahil bounded above si T dapat merong supremum. Okay? So let's call the supremum of T to be, say, M. Alright? So ibig sabihin si M ay mas maliit sa lahat ng upper bound ni capital T. Pero anong itsura ng mga upper bounds ni capital T? Ang itsura niya ay sila ay mga negative L's. Alright? So negative L, where negative L is an upper bound for T. Kasi nga, least upper bound. Pinakamaliit na upper bound si little m. Pero ang itsura ng mga upper bounds ni capital T ay mga negative L. So dapat si M mas maliit sa mga negative L. And then I will multiply both sides of this inequality again by -1, and I'll get negative M greater than or equal kay positive L. All right? But what is little l again? Little l is a lower bound for the set S. So what do we have here now? We are seeing that the number negative m, the negative of the supremum of capital T, is larger than all of the lower bounds of the set S, thus making negative m the greatest among the lower bounds. In other words, negative m is the infimum of the set S. Right? So, ibig sabihin, basta bounded below siya, na-prove na natin na meron siyang infimum. Alright? And the nice discovery that we had from this proof is summarized in remark 1.10. So nakita niyo yung corollary, sinabi niya lang na merong nag-exist na greatest lower bound. Hindi niya sinabi kung sino. Pero in the proof, we have discovered one thing, that actually that greatest lower bound or that infimum is the negative of the supremum of the set containing the negatives of the members of capital S. All right? And there you go. So parang siya yung GLB property, the greatest lower bound property of R. Pero hindi siya pwedeng maging axiom kasi na-prove natin siya using the LUB property. Axioms should not be provable using other axioms or other theorems in the system. Okay? Is that clear? Questions? Okay, mahiya kung meron kayong hindi masyadong na-gets kasi nakakahilo talaga yung pagpapalit-palit ng terms. But I hope you get the idea. All right, you just need to be careful about it. Mind all of those things, all the definitions and so on. All right? Diyan ako kinakabahan sa mga tahimik eh. So, alam nito ng mga estudyante ko, meron akong dalawang types ng tahimik. Type number 1, wala silang tanong kasi nag-gets nila lahat. Magaling kasi ako magturo eh. Hindi, joke lang. Nag-gets nyo lahat ng gusto kong i-explain. So kaya wala kayong tanong. Nakakatakot ay yung type 2. Yung type 2 kasi, wala kang matanong kasi wala kang naiintindihan kahit ano. So you cannot make any question, sensible or not. You cannot have one. So ano yan? Silence of type 1 or type 2? Or somewhere in between? Though I don't believe there's something in between. Parang continuum hypothesis ng type of silence. No? Wala talaga. Diyan ako kinakabahan eh. Pag tahimik kayo eh. Wala man lang reacts or questions, paramdam sa chat. Ito lang yung problema ko sa online. Hindi ko mahulaan kung ano yung nasa isip nyo. Kasi pag face-to-face, kind of nakikita ko na sa itsura ng mga estudyante kung nagets nila or hindi. Alam ko yung gagawin. Alam kong ulitin or i-re-explain yung isang bagay. Kaya lang sa online tayo, so tapos hindi kayo nagbubukas ng camera. Kasi actually hindi rin ako nagbubukas ng camera. So, yon. Okay, so it's fine. Kung na-absorb pa, nandiyan naman yung notes. You can read through it, okay? Or you can rewatch the recording later. Okay, pero yeah, that's a quick. I think the proof maybe is a little bit hard to follow because though it's simple, pero merong nakakalito yung mga terms na ginagamit. All right, but I hope the idea at least of the corollary and the LUB property is clear. Kasi yun naman yung gagamitin natin all throughout. Okay. Now, what we have so far is the definition of the LUB and the guarantee that any set that has an upper bound will have a least upper bound. Okay. Now, going by the definition of the LUB of a set or the supremum of a set, siya dapat ay upper bound, tapos siya yung pinakamaliit na upper bound. Sometimes it's hard also to do that because yung second condition, sinasabi niya lang, dapat siya ay mas maliit sa lahat ng upper bounds. Okay. So sometimes that's hard to quantify or that's hard to incorporate in a proof. So what we have here is an alternative characterization for the supremum, okay, which is Theorem 1.7. Ito ay isang magandang criteria para masabi ng isang number ay supremum ng isang set without going through the entire definition of a supremum. Okay, so tingnan natin yung Theorem 1.7. It says, if you have a non-empty set of real numbers capital S, then the number B is equal to the supremum of S if and only if the two statements hold simultaneously. So take note of the connective here, if and only if. Kaya siya tinatawag na characterization. Because if your number B is the supremum, then the number B will satisfy both of these conditions. And it also works backwards. If your number B satisfies these two things, then we are sure that that number B is the supremum of the set S. So parang ito yung alternative criteria para masabi ng number B ay isang supremum. So kailan daw? Dapat una muna, si B ay upper bound ng set S. Tapos, yung second condition yung crucial. Kasi alam na natin, para maging supremum, dapat upper bound siya muna. The second condition is a bit crucial. Okay? Sabi nito ay, for every epsilon greater than 0, there will exist an element of capital S, let's call it X, such that X is larger than B minus epsilon. Now, the gist of the second statement is this. Kapag ka daw binawasan mo ng katiting, all right, remember epsilon usually stands for a very small number. So it's a very small positive number. If you subtract kahit na maliit na number, even an epsilon amount, even if a very small number, to B, hindi na siya magiging upper bound. Okay, because there will be an X that is greater than B minus epsilon. Okay. So magiging supremum daw siya, sabi ng Theorem 1.7, magiging supremum siya kapag ka siya'y upper bound, tapos pag binawasan mo siya ng kahit kaunti, hindi na siya upper bound. Then you are sure that that number that you began with ay supremum. Okay. So dapat siya ay upper bound, tapos pag binawasan mo siya ng kahit na kaunti, hindi na siya upper bound, ibig sabihin siya na yung least upper bound. Kasi hindi mo na siya pwedeng bawasan ng kahit kaunti kasi hindi na siya magiging upper bound. So I think that's a nice characterization of the supremum. So ano na lang ang kulang? Kailangan natin siyang i-prove. Okay? Now the challenge here is that it is an if and only if statement. So we need to divide our proof into two parts. Kasi nga una muna, this guy implies this too, and then these two guys should imply this. Okay? So let's do the proof. Usually sa proof ng isang if and only if statement, it will be very helpful to me if you can put the arrows kung saan kayo nagsimula. All right? So forward arrow, I'll start with this guy as my premise, and I will show this. Okay? So here I will assume that B is equal to the supremum of S. Okay. And then by definition, so kailangan ko ipakita si 1 at saka si 2. But by definition, okay, by definition, then, oh, sorry, at may then pa. By definition, B is an upper bound for S. All right? Kasi nga kung siya ay supremum, which we are assuming, then dapat siya ay upper bound muna sa simula. Hence, statement 1 is already satisfied. Now, the challenge here is to prove statement 2, to show that for every epsilon, there will exist an element of X that will be larger than B minus epsilon. So here, I'll take an arbitrary epsilon greater than 0. Hold on. Okay, all right. Then, okay, B minus epsilon would be smaller than B, all right? Kasi si epsilon ay greater than 0. Pag binawasan ko si B ng epsilon, all right, magiging mas maliit na siya kay B. But since B is the supremum, it is the least upper bound. So wala nang upper bound na mas maliit kaysa kay B kasi siya na yung pinakamaliit. So this means B minus epsilon is not an upper bound for S. Kasi nga si B na yung pinakamaliit, si B minus epsilon mas maliit kay B. So si B minus epsilon hindi na pwedeng maging upper bound. Dahil hindi na siya upper bound, by definition of not being an upper bound, that means there exists an element X in capital S such that X is larger than B minus epsilon. That's the only time that B minus epsilon will not be an upper bound. Hindi siya magiging upper bound kasi may nag-exist na element si S na mas malaki kaysa kay B minus epsilon. Okay? So I think this is the easier statement kasi we are just playing with the definition of the supremum. The more challenging portion of this statement is the converse, okay? Which we still need to prove kasi nga biconditional yung statement. So we'll need to prove it the other way around. So here we will assume statement 1 and 2 and show that B is equal to the supremum of S. Okay. So by 1, we already know that B is an upper bound for S. Okay, so kailangan na lang nating ipakita na siya ay mas maliit kaysa sa lahat ng mga upper bounds nung set capital S para masabi na talaga siya ay yung supremum. Okay? Now, what can we say here? Now, gagamitin pwede natin gamitan yung statement 2. All right? So, kasi ina-assume natin na totoo yung statement 2. So, what would be a nice way to use statement 2? Magbigay ba ako ng epsilon o magbigay ako ng isang upper bound? Let's see. Gusto ko kasing ipakita na si B yung pinakamaliit na upper bound. Pwede akong mag-contradiction, pero kaya ko rin yatang i-direct. So let's see. So we will, okay. So let's consider a number B prime that is smaller than B. Okay. Gusto ko kasing ipakita na si B na yung least upper bound. Alam ko na si B ay upper bound. So we just need to show that there is no smaller upper bound than B. Because if we'll be able to show that, then we're sure that B is the supremum of the set S. So ngayon, kunwari, meron akong isang number B prime na mas maliit kaysa kay B. Okay? Gusto ko ipakita si B prime ay hindi upper bound. Para masabi ko na si B na yung pinakamaliit na upper bound. Kasi mapapakita natin na imposibleng maging upper bound ang kahit na anong number B prime na mas maliit kay B. That's the plan. Okay? But what can I use here? I can use statement 2 because we are assuming statement 2. Let's flash statement 2 quickly here. So yun sa pinakataas yung statement 2. All right. Now, since B prime is less than B, then there exists an epsilon greater than 0 such that B prime is equal to B minus epsilon. Sinabi ko si B prime ay mas maliit kay B. So, ibig sabihin, makakahanap ako ng epsilon na greater than 0 such that si B prime ay B minus epsilon. So, epsilon represents the difference between B and B prime. Okay, and it's a positive integer. Or, it's a positive real number. Okay? Now, kaya lang sabi ng property 2, sa kahit anong epsilon greater than 0, lagi tayong may makikitang member ni S na mas malaki kaysa kay B minus epsilon. Okay? Now, there's an epsilon greater than 0. So therefore, there exists, so by 2, there exists an X element of S such that X is greater than B minus epsilon. But from above, we said that B minus epsilon is exactly B prime. Okay? And what do we have here now? We're saying na lahat ng B prime na mas maliit kay B ay laging mas maliit sa at least isang member ni capital S. So that is, let's restate that. B prime is not an upper bound for S. Okay? So kahit na anong number na mas maliit kay B prime ay hindi na mas maliit kay B ay hindi pwedeng maging upper bound. Si B alam na natin ay upper bound. So therefore B must be the least upper bound. So therefore B is the supremum of the set S. And the proof. Okay? So yun yung end ng proof. Any questions? Is everything clear? Or ina-absorb pa rin? Okay, thank you for the reactions. So tandaan nyo, so ito yung pwede nating hindi daanan yung definition. Basta pag meron kang upper bound, tapos sure ka na pag binawasan mo siya ng kahit konting-kaunti, hindi na siya upper bound, then siya na yung least upper bound. So that's our characterization for the least upper bound. So dahil may characterization tayo sa least upper bound, there would be a similar characterization for the infimum or the greatest lower bound. So analogous change of words lang. So siya ay infimum kung siya ay lower bound muna, tapos pag dinagdagan mo siya ng kahit na maliit lamang, hindi na siya nagiging lower bound. If that happens, sure ka na siya na yung greatest lower bound. Greatest lower bound na siya kasi pag dinagdagan mo pa siya ng kaunti, hindi na siya magiging lower bound. Okay? Now, I think there are some nice examples here. And then, magbibigay na lang ako ng iba para sa homework para itong exercises na to ay pwede niyong pag-practicean. Alright? Para kung gusto niyo mag-practice, answer some more problems, then that's fine. I think mahirap lang dito yung part 5. Ito yung sinabi ko na equivalent yung A12 saka A12 prime. Okay? But I think these are manageable. Parang nilagay ko yata sa problem set last semester itong 3 and 4 or 3 or 4. But yeah, bigay na lang ng bago para sa homework. The homework will be available probably later tonight or later in the afternoon. Tatapusin ko muna yung 2:30 to 4 kong klase bago ko ibigay yung homework. And it will be due on Monday right before midnight again. But I expect medyo maiksi lang din naman siya. Okay. So now let's proceed to some profound consequences of the completeness axiom. And when I say completeness axiom here, I'm referring to the LUB property, okay? Which actually is equivalent din naman sa Dedekind's, all right? But I think in most of the proofs, we will use the completeness axiom, okay? The first consequence of the completeness axiom is that the set n of natural numbers is not bounded above. Yan yung una nating statement. All right? Unang corollary ng completeness axiom. Yung set of natural numbers ay hindi bounded above. So this might seem to be very obvious, but remember, we haven't proven it yet. So ngayon natin siya ipoprove using the completeness axiom. Naturally, this illustrates why we need a completeness axiom to be able to prove na walang katapusan yung set of natural numbers, at least on the right side. Sa kaliwa kasi, alam natin bounded below siya, right, by the negative numbers, right? Pero hindi siya bounded above. Let's try to prove it. And I think the easy proof here is by contradiction. So let's put here by contradiction. Okay, let's say suppose n is bounded above. Okay. Then what do we mean by being bounded above? Then there exists a real number, say m, big M, such that n is less than or equal to m for all n in n. Okay, so siya yung pagiging definition ng pagiging bounded above. Teka, dadami pala yung variables ko pag sinabi ko kagad na bounded above siya. So, replay. Kunwari, wala akong sinabi. Burahin natin yung sa recording yung last 10 seconds. So, pwede ko palang idiretso na sa LUB. Kasi si n ay bounded above, alright? Then, by the LUB property, para mabawasan yung variables kong gagamitin. Okay. The LUB property or by the completeness axiom, it has a supremum. A supremum in R. Pag meron ka non-empty set of real numbers, there will be a real number that will serve as its supremum. All right? So yun yung sinasabi ng LUB property. So this means there exists a capital M such that capital M is the supremum of the set N. Okay? So this means that n is less than or equal to m for all n in n. Okay? So dahil siya bounded above, sabi ng LUB property, meron siyang supremum. Tawagin natin yung supremum si capital M. Dahil si supremum ay isang upper bound to begin with, so ibig sabihin kahit anong natural number, mas maliit siya kay M. Alright? So yun yung ibig sabihin niya. So it follows that n plus 1 is also less than or equal to m for all n in n. Alright? Ito yung parang successor relation ng natural numbers. Pag meron ka natural number n, mag-plus ka sa kanya ng isa, siya ay natural number pa rin. Alright? Dahil si n, sinabi natin, si m ay upper bound ni n, ibig sabihin si little n ay mas maliit kay m for any for any natural number. So ibig sabihin si n plus 1, mas maliit din siya kay m. Sa kahit anong m. Alright? So this means what? So this means that n is less than or equal kay m minus 1 for all n in n. Alright? I simply subtracted 1 from both sides of this inequality. Okay? And here I'm happy because there's a contradiction. What do you think is the contradiction? Anyone? Did you spot the contradiction? Or inabsorb pa? Sige, 1 minute. Hanapin yung contradiction. Sige, kung sino makaka-explain ng contradiction, perfect na sa homework 2. Para may extra motivation kayo to answer. Anybody? Why do I say there's a contradiction already? Can you explain to me what is the contradiction? Sige, daanan uli natin yung mga steps sa proof para just raise your hand if you're ready to answer, okay? So, may contradiction. Kunwari mali yung theorem. So, kunwari si n ay bounded above. Kung siya ay bounded above, sabi ng LUB property, magkakaroon siya ng supremum. Tawagin natin yung supremum si capital M. Dahil si M ay supremum, siya ay upper bound in the first place. Okay? It is the least upper bound. So it must be an upper bound in the first place. So ibig sabihin, any natural number little n must be less than or equal to kay capital M. No question about it, I hope. All right? Dahil ito ay totoo sa lahat ng natural number n, tapos pag meron akong natural number, dagdagan ko pa siya ng isa, natural number pa rin yung makukuha ko. So therefore, since this is true for any natural number, and n plus 1 is another natural number, so n plus 1 must be less than or equal kay m. Right? Tapos paglaruan ko yung inequality na to ng kaunti. Si n dapat less than or equal kay m minus 1. Okay? Now, these two guys can easily be reconcilable, right? N is less than or equal to m, tapos si n less than or equal kay m minus 1. That seems to be fair. Posible nga siya mangyari. Halimbawa, ito si m, ito si m minus 1. Ito si m minus 1, ito si m. So, posibleng nandito si n. So, everything on that side, we are covered. That's fine. No contradiction there. But I insist there is really a contradiction somewhere. So can anybody spell out to me where the contradiction is? Dali, exempted na sa homework 2. I mean, di lang exempted, ipa-perfect ko na kagad sa homework 2. You don't need to submit a homework 2 anymore. Okay. 30 seconds. Sayang naman, oh. 15 seconds. Oh, yes, Trisha.
Hello po, rinig po ba?
Go ahead.
Sabi po kasi dun sa characterization of supremum, dapat po yung m dapat magiging greater than na siya sa supremum kapag may minus siya ng any value. Minusan siya ng any value po. Kaya naging contradiction.
Okay. Yeah, I think that's perfect. Nice one, Trisha. So you earn a perfect score in homework too. So bala ka na kung gusto mo mag-submit or hindi, but I'll give you a perfect score anyway. That's right, because we can say that it is a part of the characterization. Pag nag-minus ka ng isa, dapat kung siya ay supremum talaga, pag nag-minus ka sa kanya ng epsilon, kahit anong epsilon greater than 0, dapat hindi na siya maging upper bound. All right? But here, we subtracted 1 from m, and 1 is a perfect candidate for epsilon because 1 is greater than 0 per one of our theorems before. And yet, m minus 1 is still larger than all natural numbers. Look at the quantifier here. It's still for all natural numbers. So we're saying that m minus 1 is still an upper bound. And yet, sabi ng characterization ng LUB, hindi na to pwede maging upper bound kasi si m ay supremum na siya. Pag nagbawas ka pa sa kanya ng kahit gaano kaliit, ang laki pa nga nung binawas natin, 1 pa nga yung binawas natin, naging upper bound pa rin siya. Right? So basically, the contradiction is to the fact that m is a supremum. Okay? Or, mas simple siguro ng explanation, si m minus 1 ay upper bound pa rin. Alright? Kasi nga ang n ay mas maliit sa m minus 1 for all n. So m minus 1 is still an upper bound. But m minus 1 is smaller than m. So dapat pala hindi si m yung least upper bound. Kasi si m minus 1, mas maliit siya kay m, and yet it's still an upper bound. Okay? So in any case, you can say that the last inequality contradicts yung pagiging supremum ni capital M. Alright? And that ends the proof. So hindi natin kayang i-bound above ang set of natural numbers. And you see, LUB property lang talaga yung ginamit ko sa pagprove nito. Kaya siya corollary ng least upper bound property. Okay? Now, another nice result is the Archimedean property. So, isa to sa mga equivalent statements to the least upper bound property. So, we could have easily chosen the Archimedean property to be our completeness axiom. All right? But it is a theorem for us, and let's see why. At ano yung sinasabi niya? Sabi ng Archimedean Principle, for any epsilon greater than 0, okay, there exists a natural number n such that 1 over n, which we know is still positive, but that 1 over n is less than epsilon. Okay? So kahit na gaano pa raw kaliit yung epsilon, kaya nating makakuha ng mas maliit pa sa kanyang number by simply dividing 1 by a natural number, little n. Okay? So however small epsilon is, there is always a natural number such that 1 over n is smaller than epsilon. Okay. Let's see how the proof went. So contradiction ulit, sa tingin ko yung ginamit sa proof. So here we assume that there is no natural number n such that the inequality is true. So contradiction talaga siya. Kasi kunwari, mali yung theorem. Wala tayong makikitang natural number n na ang 1 over n ay magiging mas maliit kay epsilon. Or in other words, you can say that for any natural number n, ang 1 over n ay greater than or equal kay epsilon. Okay? And then we can multiply both sides by what? N over epsilon. N over epsilon will still be positive. So we'll get this inequality. All right? So para nag-cross multiply o nag-multiply nga ng n over epsilon. So ito yung makukuha natin. So here, what are we saying here in this statement? And remember, n here is an arbitrary natural number. So at this point, when you write this, n is less than or equal to 1 over epsilon, we are saying that 1 over epsilon is an upper bound for n. Because here, 1 over epsilon is said to be greater than or equal to all natural numbers. Okay? So si 1 over epsilon ay upper bound dapat ng n. But we know from corollary 1.1 that that is not true because n is not bounded above. So therefore, there's a contradiction to the previous theorem. So we must accept that the statement is true. Na kahit gaano pa kaliit yung epsilon, lagi nating mapapaliit si 1 over n. All right, we can always find a large enough n such that 1 over n is smaller than epsilon. Okay? May isa pang version yung Archimedean property. Mahalaga itong Archimedean property kasi gagamitin pa natin to sa mga ibang proofs later. Pero tandaan nyo lang yon. Kahit gaano kaliit yung epsilon, kaya kong makakuha pa ng mas maliit na number sa kanya. Anong number yon? 1 over a large enough natural number. Okay? Tapos, pwede ko itong paglaruan ng konti, yung conclusion ng Archimedean Principle. I can multiply both sides by n. So I'll get I'll get 1 less than n epsilon. And remember here, epsilon is arbitrary. It's any positive real number, right? And then I can multiply both sides again by any positive real number a. So magiging a less than n epsilon a. All right? Dahil si epsilon ay arbitrary, kahit anong number yan si epsilon, pwede ko siyang isulat as b over a, where b is any natural number. Kasi nga random si epsilon, pwede ko siyang palitan ng b over a. B is a random real number. Okay? So pag pinalitan ko siya ng b over a, may multiplier dito na a. So b over a times a, mawawala si a, matitira na lang ay si b. Or baliktad pala dapat yung ginawa ko. Nag-multiply pala dapat ako ng b tapos nag-divide by. Kasi ito yung gusto kong makuha. So, pero anyway, interchange lang si a at saka si b dahil si a at saka si b naman ay random real numbers. So, pwede kong i-relabel na si a, tawagin kong b, tapos si a, at tapos si b, tawagin kong a. Interchange the symbols. That's fine because a and b are just arbitrary. And this is the alternative characterization of the Archimedean property. Okay? Anong sinasabi nito? Kumuha ka ng kahit anong positive real numbers A and B. Then you can make a multiple of A larger than B. Okay. So pwede mong, lagi tayong may makikitang multiple ni A na mas malaki kesa kay B. That's what this inequality is telling us, all right? So when we talk about limits of sequences, corollary 1.2 is the better form for the Archimedean property. However, from an intuitive point of view, mukhang mas madaling maintindihan yung alternative version, yung nasa remark 1.11. Kasi pag meron kang dalawang positive real numbers, pwede mong magawang mas malaki yung isa sa kanila by multiplying a large enough natural number to it. Kasi ito, existence lang naman eh. There exists a natural number. So you can pick a very huge natural number to guarantee this inequality. Okay. And then ang proof nito, galing sa corollary 1.12, ay yung kinuwento ko lang kanina. So yung epsilon, papalitan mo lang ng, anong pinalitan ko kay epsilon? Pinalitan ko siya dapat ng A over B and so on, right? Okay. Now, let's see. Can I still prove the density property? Siguro let's stop here. Masyado na sigurong marami tayong nagawa. Let's just talk about the density property of Q and R and the rest of the modules next week. All right? So simulan natin sa density property. Pero in a nutshell, the density property says na sa pagitan ng dalawang real number, laging may rational number. Napaka-dense ng pagkakapacked ng mga real numbers. Na sa pagitan ng dalawang real numbers, meron doon nakasingit na isang rational number. Okay. Tapos the interesting thing about that is is that a rational number is another real number in itself. So ibig sabihin parang ganito. Meron kang real number X, real number Y. Sure tayo, sabi ng ng density property, na sa pagitan nilang dalawa, laging may rational number, si Q1. Okay. Sure daw tayo dyan. Lagi yung meron. Prove natin next time kung bakit yan totoo. Sa pagitan ng dalawang reals, merong isang rational. Kaya lang, si Q1 ay rational, so ibig sabihin, real number din siya. So gagamitin ko uli yung density property telling me that between X and Q1, there exists another rational number. Si Q2 halimbawa. Okay. Kaya lang si Q2 ay real number din kasi rational siya. So ibig sabihin sa pagitan ng sa pagitan ni X at saka ni Q2, meron pang isang rational number. And this process will continue on forever. Kaya parang napaka-densely packed nung real numbers. Kasi kapag kumuha ka ng napakaliit na interval, napakaliit na portion ng real number line, there are infinitely many rational numbers there. Because pag meron kang dalawang real number, sure ka na meron pang isang rational. Pero yung rational, real number yon. Sa pagitan uli nilang dalawa, makakakuha ka uli ng isang rational. And the process will go on forever. So meaning, sa kahit na napakaliit na interval, napakaliit na portion, hindi ko na siya mapaliit. Ito na pala yung pinaka-zoom. So sa napakaliit na interval ng napakaliit na portion ng real number line, napakaraming rational numbers ang naninirahan doon. So kaya napaka-dense ng real number line. Okay? A small portion of it will contain infinitely many rational numbers. So yung mga nasa Math 175 dyan, na-imagine daw nila yung bisection method. Yeah, sort of like that. Tapos hindi lang yon. May density property rin yung Q complement. So sa pagitan ng dalawang real numbers, merong isang irrational number. So ganun ganun parang napaka-compact o napaka-dense nung pagkakapack nung real number line. Napakaliit na part ng real number line, napakarami niyang laman. There are infinitely many rational numbers in there, and there are infinitely many irrational numbers in there. Okay? Pero hindi ko pala dapat ginamit yung compactness o yung term na compact kasi i-define natin later kung ano yung ibig sabihin ng pagiging compact. So pero ganun yung density niya. So a small portion, ang daming laman. Alright? And we will start there next meeting. Do you guys have any questions before we leave? Okay, so if there are none, so I'll have the second homework uploaded later, probably around 7 p.m. And deadline niya is sa Monday, 11:59 p.m. And then what else? Oh, I might not be able to meet you live on Tuesday. All right. Sige, amin na nga ako. Birthday nung pamangkin ko. So, I decided na i-treat sila to a trip. So, I'll be out of town this weekend. Uwi kami ng Tuesday. Nasa Manila siguro ako, nasa airport ng 8. So, baka hindi ako umabot. Pwede naman ako magklase habang nasa kotse. No? So, pero wag na lang. Papapanood ko na lang sa inyo yung recording nung last semester. So, yun yung gawin nyo from 11:30 to 1 kung hindi ako aabot. Pero kung aabot ako, I'll join you live. Pero if not, then I'll ask you to watch the recording nung from last semester. I'll post the link later kung ano yung timestamp. We'll start with the density property of Q and R. Tapos I think we can go until some of the special sets, open and closed sets. Pero hindi na siguro natin maabot yung perfect sets. Pero yeah. Okay, so that's it. I hope you guys will have a good weekend. And yeah, let's see each other again next week. Bye everyone. Yung mga nag-recite ulit verbally, paki-comment naman. Salamat.
Thank you po, sir.